Hey guys, so I apologize for the video cutting off. There was a technical glitch on my end, and so I'm just going to go ahead and continue with this lecture video. So the last item that was discussed was classifying solutes based on its ability to conduct electricity. And so there were two terminologies I wanted to go over. One was electrolyte and the other one was non-electrolyte. And so if a solute is an ionic compound, and when you place that ionic compound in water, it's going to produce ions. And so those ions are able to conduct electricity, allowing that electrolyte or allowing that solute to be classified as an electrolyte. And so an example of an electrolyte is sodium chloride, which is what I've written here already. And so sodium chloride is going to, if you place that in water and if you stir it around, those crystals, the crystals of the sodium chloride compound is going to dissociate to produce your sodium ion and your chloride ion. Now, one of the things that you guys need to be able to do is be able to look at a chemical formula and understand whether or not it's going to be an electrolyte or a non-electrolyte. I haven't gone over the definition of non-electrolytes explicitly just yet, so for now we'll just focus on electrolytes. And so, the textbook definition is that electrolytes are ionic compounds. So how can you identify if a compound is ionic? Well, one of the main characteristics of ionic compounds is that the cation is composed of a metal and the anion is composed of a nonmetal. So if you were to look at a chemical formula and if you were to compare the element that's written to where it's at in the periodic table, and if you find that you have a combination of a metal to a nonmetal, then you can go ahead and consider that compound to be ionic. Therefore, if you were to place it in, for example, water, it's going to go ahead and dissociate to form the sodium ion, which is a positive charge, and the chloride ion, which is a negative charge in this case. And once again, since you have a full positive and full negative charge inside a liquid solution, it allows electricity to be conducted. And so other variations of ionic compounds that you guys can, that you guys might run across are, for example, metals to polyatomic ions. So an example would be, for example, potassium nitrate. And so potassium, if you look in the periodic table, it's a metal, an NO3, from what I've asked you guys to memorize earlier on this semester, falls under the category of a polyatomic ion. And so if you were to place potassium nitrate in water, what you get is potassium ion with a positive charge and nitrate ion with a negative charge. Another variation that you guys might come across are polyatomic ions to polyatomic ions. And so, for instance, if you have ammonium, and let's just say that we have sulfate. So if you guys put these two together, remember that ammonium is a positive charge and sulfate has a -2 charge. So you probably need double the amount of ammonium to balance that -2 charge in sulfate. So here you would have NH4 to SO4. So let's just say that you have a crystal of this compound, and if you put it in water, it's going to separate into NH4 plus, and we're going to put a coefficient of 2 just to balance everything out, and it's going to produce SO4 2 minus. And so since these ions still produces that charge, this is an example of a compound being ionic. Okay. So you can have a combination of polyatomic ions to polyatomic ions that are considered ionic compounds. You can have a combination of your metal to a non-metal. That can also fall under the category of ionic compounds, and metals to polyatomics. All right, so for non-electrolytes are molecular compounds, and molecular compounds typically do not produce ions. And so if they don't produce any ions, then there's no positive or negative charge inside the solution to conduct that electricity. And so once again, very similar to what we discussed, you guys will have to look at a list of compounds and identify whether or not it's ionic or molecular. And if you've identified, so one way that you guys can identify if a compound is molecular is by looking at the elements and seeing where they are at in the periodic table. So for example, if you have C6H12O6, carbon, hydrogen, and oxygen are all nonmetals. So in your chemical formula, if you've identified that all of these elements are nonmetals, and nonmetals are typically found on the left-hand side of the staircase. So if you guys recall, so I'm drawing the outline of the periodic table here. The staircase starts from the bottom left corner at this point, and then you just kind of go all the way down, right? Just like a staircase. So everything here to the right of the staircase is a nonmetal. And so typically, if all of your elements are nonmetals, the bonding that occurs between them is covalent. And so if you guys recall from the Lewis structure chapter, covalent bonds are electrons that are being shared. Unlike ionic bonds are those electrons are fully given away or fully accepted. Since the electrons are being shared, typically those covalent bonds are strong. And so if you were to place, for example, C6H12O6 in water, and by the way, this is the chemical formula for glucose, which is a type of sugar. What you're going to get in terms of a product, is still the same chemical formula. So C6H12O6. And so notice that the reactant is the same as the product. Unlike ionic compounds, if you look at the reactant, here we have sodium chloride, and then the product is a separation of Na and Cl. And so for molecular compounds, because the bonding is covalent, which are strong bonds, when you put them in water, water doesn't really have enough, energy, if you will, to break apart these strong bonds. And so when you put glucose in water, the reason why your sugar crystals dissolve is because the individual layers will dissolve, but not the actual compound. And so if you guys can imagine sugar crystals, so this dot that I'm drawing is one glucose. So if you guys are looking at a sugar crystal, each dot is just kind of like connected to each other. And one dot is going to represent C6H12O6. And another dot is going to represent the same chemical formula. And so when you put this in water, what happens is that you get a separation of the dots. But the identity of the dot is still C6H12O6. You didn't really destroy the chemical formula. You really didn't decompose it. It just separated from its glucose neighbor, if you will. All right. And so the take-home message is that molecular compounds can be identified if all of the elements are nonmetals. Ionic compounds can be identified if you have a metal to a nonmetal, metal to a polyatomic, or a polyatomic to a polyatomic. And so if you have any of those three combinations, then that solute can be classified as an electrolyte. Whereas if all of your elements are nonmetals, then you can go ahead and classify that solute as a non-electrolyte. Cool. And so let's go ahead and further explore electrolytes. And so you guys can go ahead and imagine that solute is like the umbrella topic. So we can kind of create a flow chart. And so we can classify solutes as either a non-electrolyte or an electrolyte. And it turns out that we can further classify electrolytes based on its relative strength. And so, for example, we can have a strong electrolyte and a weak electrolyte. And a strong electrolyte is an ionic compound that dissociates 100%. So we have 100% dissociation of that ionic compound. Whereas a weak electrolyte is a partial dissociation of that ionic compound. And so when you guys are looking at the examples that I wrote above, you guys were just only able to classify whether or not that chemical formula is an ionic compound or a molecular compound. But there's really no other clues. There's no explicit clues that would help you identify whether or not the compound is going to be it's going to strongly dissociate or weakly dissociate. And so we're going to go ahead and kind of lay down some ground rules, if you will, that will help you identify whether or not that electrolyte is going to be a strong electrolyte or a weak electrolyte. So let's go ahead and take a look at the first one, strong electrolytes. And so strong electrolytes, some examples of strong electrolytes are ionic compounds that are classified as soluble salts. And so if you guys take out your solubility rules, you guys can go ahead and use those solubility rules to help you identify which ionic compounds could be a strong electrolyte. So for example, if you are looking at the group 1A elements, if you look at the solubility rules, all group 1A elements are soluble. And so elements such as sodium, potassium, lithium, if for example you have lithium iodide, LiI, since lithium is found in the chemical formula of this ionic compound. And we know that this is an ionic compound because lithium is a metal and iodine is a nonmetal. And so because lithium is soluble according to your solubility rules, then we know that if you put lithium iodide in solution, it's going to decompose into lithium ion and iodide ion. And because they are, because the positive charge and the negative charge is present, then you know that the solution is going to be able to conduct electricity. And so another way that we can identify whether or not our electrolyte is a strong electrolyte or a weak electrolyte is being able to recognize whether or not they're strong acids or strong bases. And so we haven't really gone over acids and bases, and that's going to be in the next chapter. However, we can go ahead and just list out common strong acids and common strong bases that act as a strong electrolyte. Okay. And so some few examples for strong acids are hydrochloric acid, hydrobromic acid, hydroiodic acid. So those are common strong binary acids. And then we also have other types of acids. They're classified as oxyacids, and we'll learn about oxyacids and binary acids more in the next chapter. But here we have HClO4. So this is perchloric acid. HNO3. This is nitric acid. H2SO4. That is going to be sulfuric acid. Other common strong acids, there's actually, I think it's HClO3. So chloric acid is also a common strong acid. For common strong bases, we have, for example, sodium hydroxide, potassium hydroxide, lithium hydroxide. So basically anything that is a group 1A hydroxide. Can act as a strong base. And so this is just a short list of common ionic compounds that act as a strong electrolyte. For weak electrolytes have partial dissociation of the ionic compound. In other words, if you have like 100 of a weak electrolyte, maybe like 10 of the 100 will dissociate, while the rest, the 90, stays as is. So it doesn't dissociate, it's just there. And so an example of a weak, so common weak electrolytes is hydrofluoric acid. So amongst the binary acids, hydrofluoric acid, I'm sorry, let me take a step back. So amongst all of the halogens in their acidic form, hydrofluoric acid is the weakest among them. And so we have another one, acetic acid. So acetic acid is vinegar. And its chemical formula stems from acetate. So if you guys memorize the the chemical formula for the polyatomic ion acetate. If you add in an extra hydrogen, you get acetic acid. So CH3, COOH. Another way that this can be written is C2H3, O2, and then a hydrogen. Let me go ahead and add that hydrogen in the front to represent it being an acid. Now if you wrote, C2H3O2H, it's not a common way of writing acetic acid, but the point gets across. And so, long story short, once again, if you have either of these two, these are common weak electrolytes. And so if you have like 100 hydrofluoric acid and you put it in water, only, for instance, 10 of the hydrofluoric acid will actually decompose to produce H plus and F minus, while 90 remain. Whereas for strong electrolytes, you have 100% dissociation. And so if you have 100 lithium iodides, when you put that in water, you get 100 lithium ions and 100 iodide ions. Okay. So you get a full dissociation. So you don't have any of your reactant left. You only have your products. Whereas something that is a weak electrolyte or partial dissociation, you have some product, but you still have a majority of your reactants left over. And so if you guys were to compare, the brightness of a strong electrolyte and a weak electrolyte, so for example, if you had a beaker filled with hydrochloric acid, which is a strong acid, and if you were to connect it to a light bulb, okay, so if you were to have some type of device that would measure conductivity, whether it be a light bulb or some type of electrode that spews out values, if you take this device and you stick it in a solution of hydrochloric acid, the amount of light that's being produced is very, very bright. And so if you were to compare that, so this is a strong electrolyte. And so if you were to compare that to a weak electrolyte, so for example, HF, since you have a few amount of products that, so since a few amount of the reactants dissociate to produce the products, you have few amount of the ions that has a full positive and full negative charge. And so if you were to stick that same probe that's connected to, for instance, a light bulb, the amount of light that's going to be shown is not as strong as, for example, if you stick that device in a strong electrolyte. And so we can go ahead and gauge the relative strength of strong electrolytes and weak electrolytes experimentally. But conceptually, just remember that weak electrolytes have partial dissociation of ionic compound, and strong electrolytes have 100% dissociation of the ionic compound. Okay, and so these are some common examples of strong electrolytes, and these are common examples of weak electrolytes.